This is section 5.1. Now, I have a video that basically goes through all of the chapter 5 stuff. It's the one that's solving using trig, but this is more in depth. Some of the more, going into more details. So like I have an overview video because there's so much to cover, and then there's additional details each of my other videos. So the fundamental trigonometric identities. So when I was writing this, I was thinking, well, what the heck is an identity anyway? And because like we talk about identity properties where one side is like it makes something identical, but I'm like, what does that mean as far as a property? So I did look it up, and the definition of identity in math is when you have basically one expression equal to another. So it's like a conversion factor to convert something from one form into another form. And this is really important when we use trig identities because it allows us to simplify things. So you may get something really complicated with this trig, but if you have trig identities, you can rewrite it in a way that things cancel out, and it makes it a lot easier to solve. And this is actually used a lot in calculus when you're doing derivatives and integrals of trig. So the trig identities, I would just make a separate sheet of notes of the identity, something that you can refer back to later because you're going to need it basically for every class moving forward, for all the engineering courses, the calculus courses. So it's going to be something that you're going to refer to a lot. And you would think that having gone through so much math where I needed it, I would have them memorized, but I don't. I just kept referring to my sheet rather than trying to memorize them all, because there are a lot of different identities. So we have 5 different categories of identities. The first 3 are used way more often than the last 2. So those are like the most important. The reciprocal identities, those I all have memorized. I have quotient identities memorized. I have one of the Pythagorean identities memorized, and then everything after that I always have to look it up because you don't use it as often. So just starting with the reciprocal and quotient identities, these reciprocal identities are just, you can take one function and write it as a reciprocal of another. And these were all, when you learned about, what cosecant was, it was defined as the reciprocal of sine. So these aren't really anything new from what was covered in the previous sections. It's just now they're kind of given a formal name. And then the quotient identities, when you learn what tangent is, you learn that it's sine over cosine. So it's just now it's got a formal name as a quotient identity, but these aren't really anything new. Now the Pythagorean identities, so these are new. The one on the left here is the most common. That sine, oops, I tried to get highlighter and I actually chose pen. Sine squared plus cosine squared equals 1. That is the most common identity. That's the only one that I ever have memorized. And incidentally enough, that is also how you write the equation of a circle if you are not using x and y coordinates, but if you're in what's called polar form. So that is really important to know. And just as a notation thing, if you see something like it says sine squared u or x or whatever, this is actually the sine of that thing quantity squared. So instead of writing the thing in parentheses, putting a square on it, we write the square on the sine on the trig function, but that's what it means. So that's really important to understand that notation is just a different way of writing our squares, and we only do that specifically when it comes to trig functions. So if you see the square on the trig function, that just means this the sine of the thing, the whole thing squared. So these are called Pythagorean identities because they come from the Pythagorean theorem, looking at a right triangle and a circle, and then so that's where the sine squared and cosine squared comes from. And then the other 2 come from doing some algebraic manipulation, like if you divide everything by sine, or everything by cosine, then you can put it in terms of tangent or cotangent, and so it's a way to kind of convert from one to the other. But basically, so I've got this unit circle drawn, and then I just pick some random point on the unit circle, and you can draw a triangle with a hypotenuse of 1 going to that random point with some angle u. And instead of referencing that point in terms of x and y, you can reference it in terms of the angle and then cosine and sine, because we learned that with a hypotenuse of 1, basically your x is always the cosine and the y is always the sine. So that can give you the lengths of that triangle, and then you can use the Pythagorean theorem, and that's where you get the formula, and I have it right here, but just a visual of what's going on there. So that's what the Pythagorean identities are. Most common, sine squared plus cosine squared equals 1. That's the one that you're really going to be using a lot. Then we've got cofunction identities, and so these are called cofunctions because it's a way to convert from sine to cosine, tangent to cotangent, and secant to cosecant, so hence cofunction. And these, where these come from it's actually best looked at if you graph the function and then you do function transformation. So in college algebra, we talk about horizontal shifts left and right, and you've got vertical shifts, and you've got all these things. And basically, if you do a horizontal shift by pi over 2, it will get you to the cofunction. So shifting sine either left or right by pi over 2, it actually really doesn't matter too much because just with the periodicity and stuff, but you can shift it and then it will become cosine. And so these are not used often because you don't often see functions, trig functions written in terms of like pi over 2 minus something, or usually it'll be a variable minus pi over 2. It'll actually be written the other way around. But these do exist, and occasionally you do need them. So just something to kind of put on your list. And then we've got the even and odd identities, and these are also by graphing. These are basically come from reflections. And so they're called even or odd just because basically is it, if you reflect it, is it going to be an even function or an odd function versus it's reflecting across the x, the y, if it's kind of reflecting under both. So these are just talking about reflections. And when there's a negative inside, like the negative u, that is actually telling you you're reflecting across the y-axis. And then the negative on the outside is equal to a reflection across the x-axis. So these are just showing how if you reflect, say, sine across the x, it's equivalent to the opposite of sine, or basically reflecting sine across the y. So it's just giving a different way of how these reflections work. And for cosine, because it is symmetric, so actually if I draw cosine here, a cosine is basically symmetric across the y. So that's why if you take negative u, so if you reflect it across the y, it looks identical. So it still looks like cosine u. So that's basically what this is talking about, is where the symmetry is. And so those are even or odd identities. And these are used a little bit more often than the cofunction, but not often enough that I have these memorized. I always have to look them up. So I've talked about this a little bit because just in terms of which ones I happen to remember based off of how often I use it. But we use trig identities often if we're trying to evaluate a function. So if you have a trig function, something with lots of trig and it looks really complicated, sometimes it's easier to rewrite it and it makes it simpler to evaluate. Simplifying expressions, you're trying to rewrite it so things cancel out so that it's easier to use. And factoring as well. There are times in your future courses where you will probably have to factor things that involve trig, and sometimes it makes it a lot easier if you use an identity to rewrite it in a different form. And then you can use like substitution to do a factor. So that's really where these come from. And so what I'm going to be doing for the rest of my examples is using these trig identities to show how they're used, how you can convert from one form to the other, just so you can get used to it, because you will have to do this in like calculus. So first example, we want to use the trig identities, and so we don't have to use all of them, just whichever ones we need. We're going to use the trig identities and then the given conditions to find the values of all 6 trig functions. So we know that cosecant of x equals -7/6, and tangent of x is greater than 0. So whenever I'm asked to do something where I have to find 6 trig functions, I always kind of figure out, where is this located? So tangent is sine over cosine, and if we think of our x as cosine and the y as sine, in order to have positive tangent, it either needs to be in quadrant 1 or in quadrant 3 in order for you either have like a positive or a negative over a negative, which then is still giving you a positive answer. So the tangent is either in quadrant 1 or quadrant 3. And so that kind of narrows down what we're looking at here. Now, cosecant, I need to first rewrite that, use the reciprocal identity here. So that is equal to 1 over the sine of x. And so 1 over the sine of x is equal to -7/6. So I'm going to use what I just wrote here to solve for the sine of x. So I'm actually going to, if you take the reciprocal of both sides, this is something that you may not be familiar with, but you can take the reciprocal of both sides. So the reciprocal of 1 over sine of x is just sine of x, and then that gives us a -6/7 when we take the reciprocal of the other side. So this is telling me that my sine is negative. And so if we think of sine as y, that's telling me I need to have a negative y for whatever this angle is. And so that's going to say, out of our choices, Q1 and Q3, we're in quadrant 3, because that's the only one where the sine is negative. So far we've got 2 of the 6 trig functions. We have cosecant and we have sine. And I'm going to just visualize that this angle that we're looking at, x, is right there. And so this is sort of the picture that we're looking at. And you can draw a right triangle, but we're not going to use the right triangle stuff at this point. Now we're going to use the Pythagorean identity, the other identities to solve. So in like chapter 4, you would then find the reference angle, and you can use your right triangle to figure out the other 6 trig functions. But we're going to do it a different method here, so you can see how you can also use the identities. So we'll start with the Pythagorean identity, where we have sine squared plus cosine squared equals 1, because that will allow us to find cosine. So sine squared plus cosine squared equals 1. And we know that sine of x is -6/7. So I can replace that in sine squared x, and that's going to be -6/7 squared. So I have -6/7 squared plus cosine squared x equals 1. And so then when I square, I get 36/49 plus cosine squared x equals 1. And then we're going to solve for cosine squared x by subtracting 36/49 for both sides. And using a calculator to do the fraction for you is nice. It's recommended. You don't really have to do too much. Let the calculator do fractions so you can worry about the more complicated stuff. And this gives us 13 over 49. So we want cosine, not cosine squared. So what we need to do is take the square root of both sides, and that will eliminate the square. And when we're solving anything that involves a variable and you take a square root, you get a plus or minus. So we're going to go cosine squared of x equals plus or minus, it's going to be the square root of 13 over 7. The square root of 49 is 7. So we need to determine, do we want the positive answer or the negative answer here? Because it can't be both. So if I look at my picture, the x is basically cosine. So based in quadrant 3, we need to have a negative on our horizontal. So I need to have a negative cosine. So our answer is going to be the negative version based off of the fact that we're in quadrant 3. And so we get negative square root of 13 over 7. So we've got 3 of the trig functions now. So we've got cosecant, we got sine, and then we have cosine. And so now we need to find the other 3. I'm just adding in a blank slide in my presentation here. So we can use sine to find cosecant because, well, that we already did that. Cosecant is reciprocal of sine. I mean, we can use cosine to find secant because that's the reciprocal of cosine. So I'm just going to go to this other slide here. So secant of x is 1 over, cosine of x. So cosine of x we got as negative square root of 13 over 7. So when I take the reciprocal, that's going to be a negative 7 over the square root of 13. And whenever we do stuff with trig, we always need to rationalize the denominator. So we multiply both sides, or the top and the bottom, by the square root of 13, so that we don't have that fraction in the denominator. And so we get negative 7 times the square root of 13 over 13. So we have 1, 2, 3. This is our fourth trig function, basically, the fourth one. And now we have left to find tangent and cotangent. So we'll use the quotient identity. So tangent is sine over cosine. And sine is negative 6 over 7. And then cosine is negative square root of 13 over 7. So this is the same as multiplying by the reciprocal. So that's actually the same as multiplying by negative 7 over the square root of 13. So the 7's cancel, the 2 negatives cancel, and we get 6 over the square root of 13, which then we need to rationalize the denominator. So we multiply both sides, top and bottom, by the square root of 13, and we get 6 times the square root of 13 over 13. So now we got tangent, and then we need to find cotangent. So it's easiest to just take the reciprocal of tangent. And I'm going to take the reciprocal of the 6 over square root of 13 part, not the final answer, because that will give us square root of 13 over 6, and I don't have to do any rationalizing. If I did the reciprocal of our final answer for tangent, we would have had square root in the bottom. We'd have to multiply both sides by the square root of 13 again, and it would be extra work. So if I use the reciprocal at the step before our final answer, before we rationalized, we don't have to do any of that extra work. We can just take the reciprocal. And so that gives us the square root of 13 over 6. So now we have found all 6 trig functions. And we did it using our identities. We used the reciprocal identities, the quotient identities, and then the Pythagorean identity. So are there any questions on this example? Okay. So now we're going to use the identities to simplify. So you've seen an example of how to get the different trig functions using the identities. Now we're going to just simplify. And this is the kind of stuff that you'll see in calculus, is you'll have to take the derivative or the integral of something that looks like this, and simplifying it makes it much easier. So you want to try to simplify first. So we've got tangent of theta times cotangent of theta over secant of theta. So tangent and cotangent are reciprocals, and those will cancel out. And to kind of show that that's what you're doing, we're going to take the reciprocal identity that cotangent is 1 over tangent. So I'm going to rewrite what we have. We're going to have tangent of theta times 1 over tangent of theta over secant of theta. And so the tangents cancel out, and you just end up with 1 on top of here. So we have 1 over secant of theta. Now secant is the reciprocal of cosine. So we can basically take the reciprocal of secant and get cosine, because it's already the reciprocal. You're just taking the reciprocal of both sides. But if you really want to show this, it would just be rewriting this 1 over cosine theta. And basically, you just get cosine out. So we simplify by knowing that tangent and cotangent are reciprocals, so they cancel out. And then 1 over secant is equal to cosine, because cosine is equal to 1 over secant. So you can use those identities, and then you can get cosine out. So this is how I do it. Technically, we could have skipped this this step right here, because we are given 6 identities, and so one of them is that cosine is equal to 1 over secant. So you could have actually skipped that middle step and gone straight to cosine. But I generally, like, I knew that was what it was going to be, but the most common identity that I use for reciprocal is the secant one right here. And so that's why that was what I did, is to show that step. But you can use the other identity, and it just saves you 1 step. With simplifying, there are many different ways you can get to the same answer. It's just, which identity do you think of first? And so this is what I thought of first when I was doing this, but you can get there a shorter way, and so there are multiple ways to get to the final answer. But once you get to cosine, our goal when we're simplifying is to try to get things in terms of sine, cosine, or tangent, because those are the 3 main trig functions. So as soon as you can get something in terms of one of those 3, you're good. So you want to try to get rid of any secants, any cosecants, any cotangents when you're trying to simplify. So here's one where we're going to be using that the cofunction identity here. So we've got cosine of pi over 2 minus x times secant x. So we're going to use the cofunction identity to convert this cosine into sine. So the identity is that the cosine of pi over 2, and our list has u, but you can, it really doesn't matter which variable you use. But that identity says that the cosine of pi over 2 minus x is equal to sine of x. So we can rewrite this as sine of x times secant x. And then we can use an identity for secant. So secant is basically 1 over cosine. So we can rewrite this as sine of x times 1 over cosine x. And if you multiply those, we get sine of x over cosine x. And to simplify this even further, we want to not only have things in terms of sine and cosine and tangent, but you want to make them as few trig functions as possible. So we've got 2 trig functions here. We can convert this to 1 trig function by using the fact that tangent is equal to sine over cosine. So we can simplify this to tangent of x, and that would be the most simplified version of this original expression that we got. Are there any questions so far? Okay. Here, we're starting to deal with the squared things. We've got sine squared of x times secant squared of x minus sine squared of x. So as I was writing this lesson, I went through and did all of these ahead of time because usually with trig identities and you're simplifying, it's like it takes some time because you're like, well, which one do I do? What step do I do? You know, and you can get there in multiple ways. So when I initially did this one, I kept going and got to a point where I saw that I was actually starting to make it more complicated than it was. And so that is something that can happen. And so I'm going to show you exactly what I did when I did this on my own, so you can see sort of my thinking process and how I got to a point where I'm like, yeah, I'm making this worse now, you know? And then you're like, well, what was the most simplified part before I started making it worse? So we've got multiple choices here. So we can use one of the identities, the Pythagorean identities, where we have sine squared plus cosine squared equals 1, and we can convert the sine squareds into things with cosine. Or we can take the secant squared, we actually have an identity involving that, and convert it that way. So looking at this, usually if it's better to convert one thing versus to try to rewrite 2 things. So we're going to rewrite the secant squared. And the identity that we're looking at says that secant squared x is 1 plus tangent squared x. So this is not one of them that I have memorized. I always have to look this back up. That's the one that we're going to use. And we're going to rewrite that secant squared as 1 plus tangent squared. We only have to then do one substitution versus substituting the sine squared stuff twice. So this will give me sine squared x, and then in parentheses, 1 plus tangent squared x minus sine squared x. So at this point, if you're not sure, like you're like, okay, what do I do now? Do I rewrite my tangent? What do I do? We can distribute. A lot of times with the simplifying, you're just kind of trying stuff and then seeing what happens. So When I was doing this, I thought, well, let me distribute this out, see what happens, see if things cancel out. So I multiply the sine squared x through the parentheses, and so I get sine squared x plus sine squared x tangent squared x, and then minus sine squared x. And in doing this, I noticed that the sine squared x and the minus sine squared x cancel out. So it's like, okay, great. We did actually simplify. And so that leaves us with sine squared x plus tangent squared x. And so then I thought to myself, well, can I simplify this further? So tangent of x is sine of x over cosine x. And to get tangent squared of x, you just square everything. So that's equivalent to sine squared x cosine squared x. So I thought, well, let me try to write that in and see what happens. So that would give us sine squared x. And then instead of tangent squared x, I put sine squared x over cosine squared x. And then I'm looking at this and I'm like, man, it really would have been nice if instead of sine over cosine, we had cosine over sine, because then like my sine squares would have had to cancel out. But I'm looking at this and okay, we're going to get sine to the fourth on top, which isn't really simplified. And I thought, well, maybe there's still a way that we can simplify this. So maybe I could try to rewrite the cosine and put that in terms of sine, and then maybe things will start canceling out. So I thought to myself, well, let's look at the identity sine squared x plus cosine squared x equals 1. And if you solve for cosine squared x, that gives you 1 minus sine squared x. So I thought, well, let's try to plug that in and see if that does anything here, if it starts canceling things out, or what does it look like. So I had sine squared x times sine squared x, and then 1 minus sine squared x. So I'm looking at this and I'm like, well, this is starting to get more complicated. The 1 minus sine squared x, I can actually factor. Will that allow us to kind of cancel things out? So then I started looking at that, and we will do factoring in another example, but I'm just going to show you what it would be if you factored that. You would get 1 plus sine of x, 1 minus sine of x. And I'm looking at this and I'm looking at my process and I'm like, I'm just making it worse. It's getting bigger and bigger and bigger and bigger, and nothing here is canceling out. So when you get yourself in a place like that and you're like, well, okay, it's just getting worse and everything I'm trying isn't working, go back to the most simplest part you had. And that would be after we canceled out those sine squareds and we're left with sine squared x tangent squared x. That was the simplest we had, and then everything I did from that point on was actually getting more complicated. So that is considered your simplest answer. So sometimes you try things and then you see that it's not working, and then you have to go back to what seemed to be the best answer. Are there any questions on this example? Okay. So those are some examples of simplifying. Now I wanted to do a couple examples of factoring, because I used factoring in the previous example when I was trying to simplify. And you do end up having to do things with factoring. And what we do is called substitution. When you originally learned to factor in like college algebra, you learned how to do a substitution with like u to take something that's like maybe x to the fourth and make it x squared. And you did learn some types of substitutions. And we're going to use the same thing here to try to factor this. So I look at this and I immediately know how to factor this just because I've done enough factoring with trig. But if you haven't, you're going to be like, well, how do I factor? So basically what you do is that you let u equal to your trig function, cosine of x. So that will also, if I square u, that will give me cosine squared of x. So everywhere we see our trig function, we're going to write u and u squared instead. So this gives me u minus 2 over u squared minus 4. And then you can try to factor. Because now we can see in the denominator, oh, I know how to square u squared minus 4. So we get u over minus 2 over u minus 2 times u plus 2. So when you factor that denominator, you can see, okay, this is what I got. And then you want to cancel things out. So I can cancel out my u minus 2 over my u minus 2. This gives me 1 over u plus 2. And then we need to have our answer in terms of trig. So we replace u with what we set u equal to, which was cosine of x. And so that gives us 1 over cosine of x plus 2. So you don't have to do this u substitution if you recognize that I have a cosine squared. Like what I do instead of doing this whole u substitution thing is I had a u cosine of x minus 2, and I recognize that that factored to cosine of x minus 2 cosine of x plus 2. Because I recognize that it was in that form of a difference of squares. And so I knew how to factor a difference of squares. And so I can go straight to my answer, 1 over cosine x plus 2. But if you don't really see that, and when you're learning trig, that's not something that's going to be like the first thing that you see, doing this u substitution makes it a lot easier, because then it's just in terms of algebra, and you know how to do algebra. So you just follow the algebra, and then at the very end you put your trig back in there. Is there any questions on this example? Okay. So this is my last example, and this is another one with factoring. And so this is another one where you want to kind of see how can I do some sort of substitution here. And so we've got a couple things going on here, a couple substitutions that you can think of, or other ways that you could rewrite this. So we've got secant to the 4th of x minus tangent to the 4th of x. So if you think back to your factoring rules, we don't really have anything where you factor things to the 4th power. It's usually in terms of quadratics. But we can rewrite this in terms of a quadratic. So secant squared of x squared is equal to secant to the 4th of x, because of the fact that secant of x squared is secant squared of x. And then we can do the same thing with tangent. So we know that secant squared of x equals secant of x squared. And so if you square both sides, that means secant the 4th of x is secant x squared squared, or we can rewrite that as secant squared x squared. So basically rewrite that middle part. Let me put that over on this side. So we're just turning something to the fourth power to something squared again, because that way we can factor, because we factor things that are quadratic, and that turns us into a quadratic thing. So we're going to do substitutions again here, and it's probably easiest to do two substitutions, where we can say, we can make this u, and then we can make this v, because we have two different trig functions here. So you can say let u be secant squared x, and v be tangent squared x. So this will then give us u squared minus v squared. And so this is a difference of two squares. And we know how to factor this because now we're just doing algebra. So this is equal to u minus v times u plus v. So once you factor it, now you want to put your trig back in there. So this gives us secant squared of x minus tangent squared of x times secant squared of x plus tangent squared of x. Now this looks kind of complicated, so let's try to cancel things out, try to use our trig identities to rewrite either secant squared in terms of tangent squared or tangent in terms of secant. Now generally we want to keep things sine, cosine, and tangent, so we want to rewrite the secant squared stuff. And I can definitely tell I'm going to need another slide here, so let me add in another blank slide. I'm not going to have enough room here. Okay. So we're going to use one of the Pythagorean identities. We'll use the one that says that secant squared of x is 1 plus tangent squared of x. So let's replace all of these secant squareds with 1 plus tangent of x. And it's going to get long, so I'm just going to go to the next slide. So I have 1 plus tangent squared of x, and then I had a minus tangent squared of x. And then in my second one, secant squared, and then it was a plus tangent. So we have 1 plus tangent squared of x plus tangent squared of x. So I've just replaced the secant squared with 1 plus tangent of x. And you can see that, okay, I'm going to cancel those out, and then I can add those other two together, and we get 1 in front, basically 1 times 1 plus 2 tangent squared of x, because a tangent squared plus a, oops, that should be tangent squared. Oh, oops, sorry, I could feel that sneeze coming. Tangent squared of x plus tangent squared of x is 2 tangent squared of x. So these trig functions add together just like any other things with variables add together. So they act the same way as we see with algebra. And so I'm able to combine those, and then I just have a 1 times that in front. So I get 1 plus 2 tangent squared of x. And at this point, rewriting tangent squared as sine over cosine stuff, that's not really going to help because we don't have anything else that we can cancel out. We have a single trig function, and so that's good enough. And so say this is the most simplified answer. Now, this particular problem I actually took out of the textbook, and the textbook simplified it differently. They did not substitute in one of the secant squareds, and so their answer contained both secant squared and tangent squared. And that does seem to be just as simple as what we have here, though I personally think that this is better because we do try to keep everything in terms of sine, cosine, and tangent. And so getting rid of that secant squared is just something, you know, nice. And now here, instead of 2 trig functions in our answer, we have 1 trig function. So And the book does make a point to say that there are alternate answers, because depending on what you substitute, you can, sometimes things don't necessarily cancel out the same way, but they're all kind of valid. But this is the way that I did it that I think is a little better than what the textbook did. So this was my final answer, final example of how to simplify with trig. It's kind of it's definitely problem solving, trial and error, kind of seeing where things go. And that is a lot of what math is, and higher level math is. You get to a point where, like in lower level algebra, you kind of know what to do, you learn what to do. And then once you start using higher levels of math, it's a lot more experimentation and trying things and see what happens. And I think this is a good example of showing the kind of thinking that you have to be, well, I know this, let's give it a try, see what it looks like. Oh, that didn't get me anywhere, let me try this. That's sort of what things happen in higher level math and in higher level science and engineering courses as well. You have to do a lot of, well, let's try this, see what happens kind of stuff. So are there any questions on this example or anything else that I've covered so far? Okay, so